In this experiment, I will do model breaking application for two cards moving on the track in one dimension. Let's open the canvas for reaching the report template and the experiment video. On Physics 101 webpage, and there is lab report submission section. If you click the submit report tree, Canvas will redirect you to the page. You can open your report template by clicking here. And also, you can download your experiment file by clicking here. Let's open the tracker software in our computer. And track this movie on the tracker. You see two cards on the screen that at the bottom will move with constant velocity and the upper will move with constant acceleration. Let's run the video. We are going to analyze these real cards, real motion of real video of the motions of the cards moving on tracks in a lab. We will do it by using model breaking method. The first thing is that we have to set up our coordinate system, and just pressing this corner button in your tracker will show up the axis. The vertical axis is Y and the horizontal axis is X. I will drag this origin and I will direct put the origin on that point. Once you're finishing adjusting your coordinate system, you can make it invisible by just pressing this coordinate system button again. The next thing is that we have to put the scale for position measurements. For this, I'm going to press this scale button and choose new calibration stick. The track length is 100 centimeters in this video. So we are going to mark the endpoints of the track, and we are going to state that the distance between the endpoints is going to be 1 meter for tracker. Once you have chosen the calibration stick, hold the Shift key on your keyboard and see that your mouse pointer appears to be a square sign, and then bring to the first point and mark it by pressing just left mouse button. This is going to be your first mark. And the second mark is going to at this point again to the same by pressing Shift and see the square sign and just pressing right over here. As soon as you mark the second point, the tracker will draw this blue line. I will type 1 meter between these points and enter. So this way we just select our scale for this specific video. So again, you can make this line invisible by pressing the scale button over here. And now we are ready to get the position measurements for the cards for each frame. Now we choose this create button and we choose point mass. When you do this, the tracker will form a new small window stating that mass A over here. Let's rename this by card A. This sign is going to be seen on the position measurements on the card. Before we state tracker how to get in a position measurements and times, let's concentrate on the card A. We have to choose a reference point on the card A so that the tracker will measure its position from that reference point with respect to the origin in our coordinate system. For this, I'm enlarging this card by using mouse wheel. I can choose this point on the card as the reference point to make the position measurements from the card. I can choose this point on the card as the reference point to make the position measurements from the card. In order to do this, I'm just starting with the zeroth frame. The first frame is always the zeroth frame. I will come over here on the card A and press it and just choose Auto Tracker. When you choose this select, the tracker will open up a new window. The new window is the Auto Tracker window. And then I will come over here that the point that I will choose as reference, and when I come over here, I will just press and hold the Shift key and also press and hold the Control. Now I'm pressing these two keys at the same time, holding it both Shift and Control. You see the mouse pointer appears as circle. And I come over the point that I will choose as reference and just press the left mouse button. And you see this red circle appears with the label 0 as soon as you do that. This is going to be your first measurement or initial position of the card A. The initial measurement of the card A is appeared also on this plot window, the small window next to this video on top. So just what we did is we marked the first position. And on the auto tracker window, you see these small patterns over here. These patterns are about that for every frame the tracker will look for and it will mark the center of this pattern. We will make the measurement of the position for that pattern at every frame. The rest, the tracker will do it itself. I will only press the search button, and when I just press the search button, the tracker will run the video frame by frame, and at each frame, it will measure its position from right this point that we choose as the reference. At the same time, you will see how the x versus t graph is changing on a real time. So, I'm ready to run the position measurement. The automatic position measurements to be made by tracker. So, I'm just pressing the search. You see what happens. The tracker in each frame, it just measures the position just from the front of the card A until the last frame. There are 14 frames. So, all our measurements are done now. What the tracker has just done now in a very quick time, it measured 14 position measurements on this card. And you can also see these measurements on the plot window, X versus time graph. You can also see these measurements in a tabular form on this third window, the table window. There is also Y column about Y measurements. Y measurements don't change at all because, as you know, there is no motion in the Y direction. The tracker is measuring the position of this card, and every frame, if you run it frame by frame, you see. But what about the errors in these measurements? There should be error on this measurement because no any device can make measurements without errors. When you look at this enlarged screen, enlarged picture of this card, you can notice that these squares are the pixels in your picture. So these pixels are the smallest visual information about the picture of the card. So you can take the length of the smallest squares, the pixels, to be your position measurement error. The error in your position measurements. Because every picture in a video consists of these small pixels and we don't see them when we look at the normal picture because they are too small, but when you enlarge it, you can see them. You can see them that every picture is formed by just a collection of these small squares. So it's very logical to take the length or the size of these small pixels to be your position error done by the tracker, because the pictures are formed by these pixels. So, as you know, for every frame, these pictures are remade for each frame following this motion of the card. And the possible error is going to be once the size of these small squares. The next thing is how can we measure the size of these each squares? To do this, we have another tool again. We come to create button and come down on measuring tools. On the measuring tools, just select tape measure. When you select tape measure, you will see this line stating its length from one end to other end appearing. You can direct the ends of this line so that you can bring them to any 2 points that you want to measure the distance. Let's do this. Since every squares every pixels are very small, what I will do is just that I will, for example, start from 1 pixel from here, and I will count, let's say, 10 of them, and come to 10, and I will just place these endpoints from the starting to the end of these squares and measure it. While measuring it, just look at this number and then record them and divide this by 10, because I'm just measuring the length of 10 squares. And if I divide this by 10, I will be able to just measure the size of one single square. So I'm choosing this one as the starting square. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this one is the end square. So I just place the end points over here and over here. The distance is the size of 10 squares, 10 pixels, and it just reads 1.455 times 10 to the minus 2 meters. So if I divide this by 10, it's going to be 1.455 times 10 to the minus 3 meters. It's the size of one square. And this is going to be my delta x, or the error in position measurements made by tracker. Let me write this over here. This is the error in position measurements made by tracker. What about time measurements? Time measurements are done by just counting these frames, and if you come to this movie button over here and press it, you will see this some frame information about this movie. It is 15 frames per second, and each frame has a time duration of 0.067 seconds. So, if this is the timing for only one frame, then this can be taken as the time error in time measurements. Let's write the error in my time measurements. I will record this as half of 0.067 means 0.034 seconds. For this is my error in time measurements. So this is my error in time measurements. After determining the errors in measurements, I'm ready to analyze the data produced by tracker. This is the tabulated form, and this is the visual form. So I will make a model breaking now. First of all, what is our model? Our model is already there. The model is this. The position is just a parabola in time. It is x0 plus v0 times t plus 1/2 at squared. So the model is this one because it's already known for model breakings. The models are not made, but they are already there. And what we do is just we try to make this model unique for our case by just determining the parameters. In the parameters, in this constant accelerated motion in one dimension is just, we have three parameters: the initial position, the initial velocity of the cart, and its constant acceleration. So, what we will do is now that we are going to determine these parameters, but how are we going to do this using our data? Let's come to the tracker screen. This is our data. What we will do is that we are going to determine these parameters by analyzing this graph. Come over the graph, just press the right mouse button anywhere on the graph, just select Analyze. So the new window will arise when you do this. You will see again these data points, but they are connected now. What we will do over here, we will make a model breaking by using curve fit. If you select curve fit, the tracker gives this button windows, inner windows. You will see this fit. What we mean by curve fitting is that we are trying to determine the analytical function best fits to our data. But when you look at this data, it looks like a parabola. It's going to be a parabola because the model is already there. I said it is a constant accelerated motion, and for a constant accelerated motion, the position is a parabola in time. So we are going to choose from analytical functions a parabola. Parabola is over here. As soon as you choose parabola over here, the tracker will draw. It's already drawn in the color of pink over there. The tracker draws the best parabola that fits your data. The tracker gives parabola equation as x equal to at squared plus bt plus c. What these ABCs are? In our model, this is A, this is B, and this is C in the tracker. That's what the tracker sees. It already determined these values because it fits the data, and A is calculated to be 8.601 times 10 to the minus 1 meter per second squared. And of course, this is half of the value of the acceleration from our model if you compare at squared. B is there and C is there. They are calculated or fitted by tracker. So let's determine initial position, initial velocity, and constant acceleration. So when you look at these parameters determined by tracker ABCs, we just figure out that initial position is 8.526 times 10 to the minus 2 meters. And initial velocity of the cart is 1.433 times 10 to the minus 3 meter per second. It looks like 0, but you know the tracker is very delicate in calculating these kinds of things. And the acceleration it calculated to be 1.720 meters per second squared. So we just figured out what exactly the position function of this card as a function of time calculated by just doing this curve fitting. So we have just let the tracker analyze the data and it found the best fit parabola for our data and just calculated all the values. Are we done? Of course not, because we have to calculate the errors in our results. So, what's the error in the initial position? The error is the measured error, which is delta x. You can always write this over here, x0 plus minus delta x to be. It's going to be 0.146 meters because I will record this x0 to be 8.526 times 10 to the minus 2 meter. Well, after the decimal, you have to be careful that we have only 3 digits in the result. So, the error must have 3 digits after the decimal point. So, it's going to be 0.146 times 10 to the minus 2 meters. So, we have to, as you know, find the error values. The tracker has these measurement errors. It just funds this model with all the parameters. How do we know that this model successfully explains the motion of our cart? When you go back to Analyze window on Tracker, you will also see this thing that it says root mean square deviation. It has just calculated the number as 6.901 times 10 to the minus 4. What is that root mean square deviation? The root mean square deviation is a kind of measure of distance or difference of all the data points to the parabola that the tracker fits as the best curve to your data. The best curve is analytical function. You have sets of data points and some of them are going to be just on the line, and that's okay, but some of them will be just off the line to a degree. But it seems that all the data points look like that right on the time, but it's not in fact. If enlarge this picture, as you know, some data points are just off the lines. How are they going to measure this difference? When you look at a certain data at a certain time, just look at its position value, whatever this position value, and this position value of your real data is of the curve by how many millimeters, let's say. What the tracker does, it calculates all of these differences and it gets the mean value of it. So the mean value of these differences of each of your position of your data to the best curve fit is this much. And this is in meters. You can read this as 6.901 times 10 to the minus 4 meters. Well, how are we going to use this number to justify the success of our model with these parameter values? The success of our model is to be determined by just looking at this root mean square value and comparing this to the measurement error, which is made on x, the position measurement value, which is delta x, 1.455 times 10 to the minus 3 meters. Since this RMS value, the calculated error, the average error, is smaller than the measurement error delta x, we can safely say that this model successfully explains the motion of the cart, because the root mean square errors for each data, average errors for each data, is less than the measurement errors. It is within the measurement errors. That means the best parabola fit is just within the measurement error made by the tracker. So the root mean square always must be less than this measurement error delta x. In that case, you are safe. You can safely say that your model with these parameters successfully explains or fits to your data. This is how we justify the success of our model by just looking at this root mean square value, whether it is smaller than the measurement value in using the same units. This is smaller than our position measurement errors, then you are okay. Next, I will continue to determine the errors in these parameters. We have already done the position. The tracker calculated the initial velocity value, but what about its error? V0 plus minus delta V. What's delta V in this result? The tracker is calculated its initial velocity, but what is the possible error in this result? As you know, in physics, we don't only have errors in measurements, but we also have calculated errors in results. If there are, of course, errors in our measurement, there must be errors in our results. So, what is delta V? How do we get this delta V information? For this, let me switch to the tracker screen again. I will just choose this XT analysis window. I will open V versus T graph because we are concerning the velocity now. When you change this plot window, V versus time from X versus time, V versus time will show you how this velocity of this cart is changing over time. Obviously, for a constant accelerated motion, this should be a straight line with some slope. The slope of this line, of course, is going to be the acceleration. Another way of calculating the acceleration is just by looking at the slope, but we've done this already by using x versus t graph. So what we are going to do again, we come over here again and press the right button of your mouse, come to Analyze. I will open up a new window. We will come to Analyze. Again, curve fit. Now this time we are curve fitting V versus T values. But V values over here are not data. They are calculated data. They are calculated by using position and time measurements. They are calculated by tracker. These points can be taken as data, but it is not direct measurements. It is calculated data. Again, when we come down to this root mean square deviation, what the tracker has done just again to produce the best line for this data. As you know, it calculated A and B parameters again, and A parameter is just the slope of this line, which is the constant acceleration. But we have already found this constant acceleration 1.720 meter per second squared. It calculated this constant acceleration as 1.719 meter per second squared. They are close to each other, but we don't get the acceleration information from here because we have already done it. What about this root mean square deviation? This root mean square deviation is just to be taken to be errors in this velocity calculation at each and every frame. So I will take this value, which is the root mean square deviation for this graph, which is in units of meters per second, to be my error value in velocity. This is calculated as 6.364 times 10 to the minus 3 meter per second. Let me record this value. What next is to find the error in the results of calculated acceleration. What is delta E? This is the calculated acceleration by the tracker, but we must also know what is the error in these results because we are using values which are by themselves have errors. To calculate error in A, first let me solve A in this equation in terms of other values. If you solve A, you will get 2 divided by t squared times x minus x0 minus 2v0 divided by t. This is an expression for acceleration by using this equation. Since we have an equation for acceleration now, if you have an equation for a quantity, and then you can calculate the error in that quantity in terms of the errors of the variables that give this quantity over here. So we have over here x, position measurements, t, time measurements, and v0, calculated initial velocity. So if you know the errors of delta x, delta t, and delta v, you can calculate delta E. The first thing you have to look at over here is that the acceleration is sum of two expressions, just like let's rewrite the acceleration as sum of u minus v. We just call this term 2 divided by t squared multiplied by x minus x0 as u and 2v0 divided by t as v. So, if you have errors in u and v because you have errors x, t, and v0, you can calculate delta A. In the formula for this, if you know delta U and delta V, delta A is going to be delta U squared plus delta V squared in square root. The next thing is that we have to calculate what is delta U and what is delta V. What is U? U is 2x minus x0 divided by t squared, and if you know u in terms of x and t, you can calculate delta u in terms of delta x and delta t. And this has a formula. This formula is 2x minus x0 divided by t squared multiplied by delta x divided by x squared plus 2 times delta t divided by t squared in the square root. So, what about x minus x0? X minus x0 just the distance from the starting position of the card in the video to the last frame. X0 is going to be 8.526 times 10 to the minus 2 meters. And this is going to be whatever you see x0 over here, you can just put this value instead of x0. And we know what delta x. Delta x is already calculated, already found in terms of the meters in this value. And what is delta t? Delta t is there, already calculated by the half of the frame duration in our earlier part in this video. And what is x and t? X and t are the last position and last time measurements, respectively. Let's check what they are in our tracker. Come over here, change this to x, and just pick up the last position measurement and last time measurement from the data table. The last position measurement is 0.835 meters. So x is just to be taken as this, and the last time measurement is 0.933 seconds. So t is just to be taken as this. Let's record this. So all you do is just put these values, calculate delta U. And again, let's express also delta V's. Since V is 2V0 divided by T, delta V is going to be 2V0 divided by T multiplied by delta V divided by V0 square plus delta T divided by T square in the root. So, what is V0? V0 over here, the initial velocity, and delta V is calculated the error in V0. All the values are clear now. The next thing is that we will just putting delta U and delta V on the formula delta A. The next thing that we will just putting delta U and delta V on the formula delta A. I know it's a little long, but this is how to calculate the error in acceleration. I just calculated this. As a result, I just found this as 0.1263 etc. meter per second square. So the result of the acceleration information should be 1.720 plus minus 0.126 meter per second squared. We write delta A in the same form as the A with 3 digits after the decimal points. The next thing is doing the similar things for the card B. We will analyze the motion of the card B again using the model breaking method. We done this analyze in our previous experiment, the motion in one dimension with constant velocity experiment. So I will analyze this motion until the collection of the data. After that, you should continue analyze the motion of the card B with using model breaking method. In this method, what you should do is that you should analyze the data by curve fitting and also do error analysis and decide whether your model is successful based on the error analysis and etc. If you will have any problem with this, you should watch the second experiment video. So, let me bring the video to the 0th frame. Since we use the same video, the error in the position and time measurements will be the same. Let's choose this create button and then select point mass to introduce the card B. Let's rename this by card B and choose the color as blue for the card B. As you know, we have to choose a reference point on the card to measure the position of the card according to this point. Before that, just come over here on the card B and press it and just choose Auto Tracker. And again, come over here, that the point that I will choose as reference, and while pressing and holding the Shift key and also the Control key, press the left mouse button on the reference point. We done the initial position measurement of the card B. Press search button to the automatic position measurements to be made by tracker. You see the time measurements and X measurements here and here for the card B. Now you are ready to analyze the data produced by the tracker for the card B. You should continue to analyze the motion of the card B. I will continue for the next thing. The next thing is about the comparing the motions of two cards. What we will do is that we are going to compare the motion of the card A and card B. For this, I come over the graph, just press right mouse button anywhere on the graph and just select compare with. After this selection, a small window opens. As soon as I mark the card A selection on the opening window, the data of cards A and card B is seen in the same graph. So, the motion of two cards can be observed and compared by using this graph. You can also see the motions of the cards with the data points on the plot. That's all we have done in this experiment. The next thing is about preparing the report. For this, you should use the report template shared with you. Let's go to the report template. First of all, you should answer the pre-lab questions. And there is an abstract. You should write the abstract with your own sentences by reading directions. Introduction is about the motion in one dimension with constant velocity and constant acceleration. And also there is an information about the tracker software. You can skip introduction part just by reading. Objectives are about what we will do in this experiment. Our equipment is here. In the procedure part, we are talking about on the section 3, fill out this report template with your results and submit. For submission, you have 2 weeks. There is data and plots part. First thing is that you should measure the pixel size, which will be the error in your position measurement. I've told how you measure the pixel size, but you can also use this link to see how you can find this. Second thing about your tables, you should put your tables containing time, position, velocity, and acceleration data here and here for the cards A and cards B respectively. Let's take a copy of data table for the card E together. For this, let's go to the tracker. Let's choose card E and just click the table and choose X, Vx, and Ax. Remove Y and close. Click the right mouse button on the table anywhere and click Copy Image. After that, you have to change this table to yours. You have to change all the tables and images with yours. Let's take the picture of compare with x versus t graph. You should answer all the questions in your report. And you should write the results and conclusion parts with putting your answers.